Hi, my name is Rahul, and I'm joined here by my partners Maggie and Scott. For our NLP project this quarter, we've decided to create an automatic speechwriter. By that, we mean that we want to emulate a real human speechwriter. For example, a public figure could provide a set of desired objectives for a speech, along with the emotion they wish to convey, and their speechwriter could write a first draft of a transcript for them to review and possibly use. To do this programmatically, we're utilizing the GPT-2 model developed by OpenAI because of its immense success in language modeling. Its power comes from the transformer model that underlies this and many other popular models like BERT and T5, but it's implemented as a large stack of only the transformer's decoder modules. This makes GPT-2 a unidirectional language model that can accept a sequence of words and produces what it thinks is the most likely next word in that sequence, like you can see in the example image below. To utilize GPT-2, we take advantage of transfer learning via the pre-training and fine-tuning paradigm. Beforehand, the model has already undergone zero-shot learning, which means it was trained on a large corpus of just general text, not necessarily specific to any task. We will then apply the pre-trained model to our task by training it again on our speech generation dataset, which essentially fine-tunes it for our task.
So next, we'll move on to the implementation steps. Here is an overview of the 5-step pipeline, which we'll go over in the following slides. We first generate a summary and analyze the tones of the acquired speeches as metadata, before fine-tuning them with speeches as label using GPT-2 medium. The end results are auto-generated speeches once we input summary and tone. We analyze the results using both test data and summary we came up by ourselves.
To gather our data, we scraped speeches from an online speech bank on a website called American Rhetoric. This gave us around 1,200 speeches, most of which were from the 1900s and onward, that contained the speech title, the speaker name, the year the speech was delivered, and the transcript itself. But for our current model, we're only using the transcript alongside our generated summaries and tones, which we'll talk about in the next few slides. We also have access to a data set of just presidential speeches that we also want to experiment with.
So to generate a summary, we use 3 different methods that are either extractive or abstractive. Word frequency summary mainly extracts the sentences with words that occur most frequently in the text. T5 and BART are 2 recent abstractive summary methods proposed by Google and Facebook AI respectively. We applied and compared the outputs of 3 T5 models and 2 BART models of different sizes. T5 stands for text-to-text transfer transformer, and it combines the best of existing transfer learning techniques. The highlight is that it can reframe all NLP tasks into a unified text-to-text format. It uses the same model, loss function, and hyperparameters on a diverse ranges of tasks. We first explored T5 for document summarization. We ended up using BART summary for downstream tasks. BART essentially generalizes BERT and GPT training schemes, combining bidirectional encoder and left-to-right decoder. It is fine-tuned particularly for text summarization. Here on the top right are the sample summaries generated for the same speech. The average summary lengths are 50 words.
We realized, though, that the summaries we were generating often lacked the style of the original transcript. So we decided to augment our data further by explicitly generating the tone of the speech to include in our training. To do that, we utilized the IBM Watson Tone Analyzer, which is implemented as a support vector machine trained on various explicitly selected features. This gives us a list of 7 tones listed on the right that we could associate with each speech.
As previously mentioned, GPT-2 uses causal language modeling, which means that each token is predicted only from previously seen tokens. In order to train our model, we simply organized each data sample into a sequence of ordered fields: summary, tone, and speech. We then add special summary, tone, and speech tokens to identify the beginning of each section and fine-tune GPT-2 to predict each token in the data sample given the previous tokens. This slide presents an overview of our pipeline for fine-tuning GPT-2. We utilize the Hugging Face Transformers library to download a pre-trained GPT-2 model and fine-tune it on our clean dataset. This produces a model capable of generating presidential speeches when given a summary and tone. We can then draft a summary and tone and use top piece sampling and top case sampling to generate the speech. We will now briefly go over some of our results. Here is an example speech generated from a summary in our test dataset. The summary mentions discrimination and that the Department of Education should protect all students. The generated speech refers directly to the Department of Education and examples of discrimination. Here's another example speech generated from our own summary and tone. So the model never saw this during training. The summary mentions both the volatile stock market and hygiene. The generated speech refers to both a stock market crash and the need to look after our health. In conclusion, we successfully trained an automatic speechwriter capable of generating reasonable speeches when given summary and tone as input. We found that our fine-tuned model had a reasonable perplexity score of about 18 on our test dataset, while the pre-trained model had a score of about 22. Future work could incorporate larger models, such as the recently released GPT-3, add more training data, and expand speeches outside the domain of politics. Thank you.